Good morning, everyone. It's a pleasure to be here, and I thank Jan and the organizer for inviting me. The idea I want to convey today is that there is no such thing as a long-term slip rate on a fault. It's not a new idea. It's something which has been seen in many different data sets, but the earliest one maybe is the paleoseismology and historical seismicity. Back in the 70s, Ambrose noticed that the cumulative count of devastating earthquakes on the eastern where's the pointer? Oh, it's here. On the eastern Anatolian fault and the northern Anatolian fault was alternating, and there are periods of high activity on one of them, was the other one was quiet, and vice versa. So should we have, at that time, if we had GNSS vector data or INSAR data, what would be the apparent slip rate accumulating on the deep part of the fault during these periods is a legitimate question to ask. But unfortunately, we didn't have any data there, and only time will tell us how these faults behave on that point of view. So I want to show another example, which is kind of the same idea on different timescales. It's a northern Mojave area in the western US. You have the San Andreas fault here, the Garlock fault here, which is an oddity in a right lateral shear zone. This is the only left lateral fault in this right lateral system. And the Eastern California shear zone, which is here, which is an array of right lateral faults. And if you look at the past seismicity, which is recent seismicity on the geological timescale, this system is quite active. You have the Owens Valley earthquakes in 1872 and the two Landers earthquake and Hector Minor earthquake, which are well known in the south here. And during that time, nothing happened on the Garlock fault. However, the geological rate on these faults is showing a different picture. The rate on the Garlock fault is something like 7 millimeters per year. And all these faults in the Eastern California shear zone, at least the Mojave sections, are sub-millimeter per year. Or I think the fastest is the Blackwater Calico fault here, which has a rate of 1 or 2 millimeters per year. So it's very, very slow rate. And none of them cut through the Garlock fault. And during that time period, nothing happened on the Garlock fault, seismically, nothing significant. So we had the first INSAR. This is really the beginning of INSAR. In the years following the Landers earthquake. And we were looking at data to try to estimate the slip rate on the Garlock fault. And to our surprise, nothing showed on the Garlock fault, nothing resolvable within the noise of the data, but we could see a shear zone connecting the southern tip of the Owens Valley earthquake to the northern tip of the Landers earthquake. So that was very surprising. And if you look at the same data set in cross-section, you see that it was even very consistent with what we could see on the GNSS transect here across the Walker lane, showing a concentration of strain in this area, which was interpreted by Gan and his co-authors as possible post-seismic relaxation due to the Owens Valley earthquake, which could be, but it's pretty much more than a century after the event. So the interpretation of this is that these faults have rates that change over cycles that are much longer than the return period of these earthquakes. And there is some kind of alternation. I don't know how alternance is not an English word, but that oscillates between the right lateral and left lateral fault system in this conjugate setting. So when I mentioned that to Paul, he said, well, conjugate faults exist in nature. And here's an example. I don't know if you ever flew in an aircraft with Paul, but when he's in an aircraft, he's always the nose stuck on the window. He cannot stand to be on the seat, which is not on the windows. And this pictures was taken on a flight over Iran somewhere, southeast of Tehran. And it shows beautiful anticline that are actually offsets by structurally faults. And for those of you who didn't realize this, but they are conjugate fault systems. And something happened somewhere when these faults interact, but unfortunately, it must be a low in the topography because it's all covered with laterite, so that nothing you can see. But these faults interact and must cut one another, and we can see that in little experiments, and you recognize the colors of plasticine. And you see that there are branches that are offsets by subsequent movement on the conjugate part, and there are some kind of oscillation observed in the system here. So there may be something like that there. So going back to Tibet, Paul was first and foremost a field geologist, yet his first steps in Tibet were through the lens of the Landsat optical instrument. This is something which was recalled by several speakers yesterday. And this is an example of the type of mosaics that Paul laid out on the floor of his office in Montpellier. These little imagettes of 1 to 1 million scale of Landsat, and he was on his knees and hands with Meteor, like kids playing, and he was drafting the maps that we know now are the maps of Tibet. And all this work set the framework for our current understanding of the tectonics of Asia as it was recalled yesterday. So given the difficulty of access and the size of the Tibet collision areas, it's not a surprise that space-based technology really played an important role in the understanding and the further understanding of what's going on in Tibet. And we mentioned the deployment of several and now thousands of GNSS instruments in Tibet, and of course now with the advanced end of INSAR. So I'm going to talk about INSAR now and the recent result we obtained. So this is the data set. So it looks like similar to what we've seen yesterday with Tim and Anne Reddumas. This is done with Sentinel-1 data. This is a partnership with JPL and REI, which is an organization within JPL which processes automatically some data. So the processing is done automatically by REI to produce in the programs, and then we stitch the frames together on long strips and tie them to the GNSS vector. I'm not going to spend too much time on explaining that. I think it's pretty similar to what Tim's presented yesterday. The major difference is that instead of tying each frames to the GNSS reference, we tie the long strip of 1,500 kilometers or more across the entire plateau. So here we are looking at the east component of the velocity field. This is the best horizontal component constrained by this system. Unfortunately, it's not designed to measure the north component, so there are a lot of things we cannot see, especially in the west part of the plateau. So I didn't have time to present an early version of this to my dear friend Paul. I had a meeting with him on the summer of 23, and he had to leave early from Paris to go to Annecy, and I never had a chance to show him. This is a big regret of my life, but he would have been thrilled to see that the fault that he carefully mapped during his PhD fell really very nicely on the region that you could see on the previous slide, where the velocity, the color change, actually, it's where you have a velocity gradient, and it's amazingly how accurate these maps are. Of course, the Altintag and the Kunlun stand out, but also several branches of the Kunlun system here on the eastern Tibet correspond also to subtle changes of colors, which indicate shear in this map.
It looks as if Kunlun fault has a higher slope ramp. That's simply because it's an east look and there's a northern component to the Altintag?
It could be, but I don't think that's the reason, and I'm going to talk about this. Kunlun fault has been very seismically active, not the Altintag. So the before slide was the slide just before was the east component, but there is a component which is interesting for this case, is the GNSS parallel component or the magnitude of the horizontal vector. And it's interesting to notice that in the ITRF 2008 reference frame, the GNSS vector nicely aligned with parallel to the direction of the main fault. So we thought that this was a convenient reference frame to work with. So that's what we used is the, and when you compare the GNSS vector with the INSAR data, the agreement is pretty good. We are within 1.61 sigma differences between the two data sets. So I'm not going to comment too much on the general things. The team writes did that yesterday, but obviously the major fault highlight here, and as Ross noticed, that the Kunlun fault is actually conspicuous in the middle of Tibet. And there is a reason. It has been very active seismically, and there is still some post-seismic movement going on. In southern Tibet, there is a stepwise extension, which is actually nicely shown here on the Graben, the Gulu, Bengso Graben system, which is here, and it seems to propagate to the north. So it doesn't seem like the extension is so smooth. I would respectfully disagree with Tim. I think it's more like a stepwise extension in southern Tibet. But I'm going to concentrate here on the strike slip fault to the north. So when we look at these data sets in a different way by tracing very long profiles, more 1,500 kilometers or more, perpendicular to the GNSS vector, that's what we see. Flat zones and shear zones, flat zone, shear zones. And I would also disagree that I do not see there is much room here for distributed deformation between the major faults. It's only showing the shear. It's not showing the extension. It's the shear because the profiles are all perpendicular to the vectors. But this is really flat shear, flat shear, flat shear. So you see here that the Altötag is fast on the western side. This is west to east. And then its rates decreases. And the Kunlun takes off, in the middle of Tibet here in a very spectacular manner. So the seismicity in the recent past was concentrated, as I mentioned, on the Kunlun fault, and this is why it's probably so conspicuous in the middle of Tibet compared to the Altötag, and I'm going to develop that a little bit more. And these earthquakes were preceded by two magnitude 7 plus in the 19th century, 20th century. So this fault has been really, really active, and during that period of time, the Altötag was more or less silent, except recently on the west side, but there was nothing above 7 along the entire fault length. So looking in more detail at the slip rate along this fault, this is a sequence of a subset of the profiles we run across the fault. And to make it very simple, we adjust this A-tan function that you recognize here to determine the slip rate and the locking depth along different sections of the fault. So that's what we see. There is a decrease from west to east. There is some kind of, I would say, something I don't really understand. We don't really understand here on the western part, which seems to indicate a rate which is in excess of previous estimate that we had with the work done by Simon Duke with ERS and VSAT data. But for the rest, it's pretty consistent with a rate that decreases from about 10 millimeters in the west to a few millimeters per year on the east side. So if you look at that, and if you collapse all these data sets on a plot, I want to make a first point here is that the slip rate decreases in two steps along the strike. It starts with a relatively high rate at 10, 11 millimeters per year, and around this longitude, it drops to about 5.5 or 6 millimeters per year, and then it drops again in the eastern part where the fault branches into the thrust fault in the Chilean mountains here on the northeast part of Tibet. So that drop in velocity is understandable by the connection with this fault, but for the drop in velocity in the central part, this is a little bit of an enigma because there is no major fault connecting directly with it. There is just the presence of the Kunlun fault below. So Second point I want to make is that, well, from that, we could say that this central part of the Altinitag is in the shadow of the Kunlun Fault. That's the main point I wanted to do. But this is a little bit of a problem on a long term, because if you have a restraining system like this, the slip goes from the Altinitag on a right step to another left lateral system, you expect some compression in this area, and we don't see any topography in this area. So it's not a sustainable configuration. But for the moment, that's what we seem to see in the subrates of the fault. So the second point I wanted to make is that it seems like the central part of the Altinitag had a slip rate decreasing after the Kunlun earthquake. And this is just by comparing the pre-Kunlun GNSS estimate of the slip rate. This is a work that Roger Bilham will recognize from his former students, Rebecca Bendick and Kelly Wallace. And both studies actually confirmed that the rate was on the order of 9 millimeters, 10 millimeters per year on that section. When we look at the radar profile that corresponds to this section, it's really difficult to make more than 6 millimeters per year on this. And the noise is very small. I think it's a little smaller than the GNSS data. And the model fit quite well. It doesn't mean that the model is correct, but it means that we cannot do more with this data set and this model. So that's the second point I wanted to make, is that there may be a response of the Altinitag to this seismicity that occurred along the Kunlun Fault over the last 100 years or so. So looking at what's going on the Kunlun Fault during that period of time, it's interesting. And that's probably what Ross was pointing at, is that it seems to go faster than the Altinitag. It definitely goes faster in the Altinitag, especially in the near field. So you notice that these profiles are not the normal ATAN function that you expect for locked fault, but there is something happening on the fault which is actually increasing the near field velocity between the two sides. And if you model that in a way, a very simple way, what I did here is I removed the long-term 11 millimeters per year, which is well established on the Kunlun Fault from the data. That's what we get. That's the residual. And that we can say that this is the transient signal that we want to model. And we model that with two ATAN functions, the difference of two ATAN functions, one of them constraining the top of the creeping part, and the other is constraining the bottom of the creeping part. And what you get when you do this kind of inversion, it's a kind of a patch of the fault right below the seismogenic depth, which can creep at a very fast rate. And you can notice here is that the darkest color here corresponds to about 10 times the sleep rate, the long-term sleep rate. So this is quite amazing, but that's what you need to produce this kind of bump near the faults here. So whether it's afterslip, viscous afterslip on the deeper part of the fault, or kind of distributed viscoelastic relaxation, it's a question, but it must be close to the fault to maintain such a steep gradient at the fault. So if you look at that figure compared to Cécile Lasserre's post-seismic solution of the recent Kunlun earthquake, you notice that the co-seismic slip occurred down to a depth of about 15 to 20 kilometers, and that part of the fault, the patch of this fault, which is activated since then, is really bordering quite nicely the base of the seismogenic zone here, the part that broke during the 2001 earthquake. And this is pretty amazing to observe such a fast rate so long after the earthquake. The Sentinel data started in 2014, which is already 13 years after the event. So we have very, very fast afterslip depth. So whether this contributes to slowing down the Altinitag is the question I'd like to answer in the coming year. This is a thing that's a good suggestion. Okay, so that's what I wanted to say. And No, I had something else. Sorry, I forgot. This was done with the mean velocity over this 8 years period of Sentinel data. But if you look at the time history of the displacement, you can do that, because when we estimate the mean velocity, it's estimated from the time history of the displacement. You look at movement of A with respect to B, that's what you get. So over the time period we observe, there is not much curvature, there is not much change but we can see a hint of a curvature along this fault. And we can convince ourselves that it's slowing down, but we're going to have 20 years of Sentinel data, and NICER data, so we're going to have that much longer. But over that period, if you estimate a relaxation time, you get something like 25. If you fit a log function instead of an exponential function, then you get something like 21 or 22 years. It's very similar. So that's the type of relaxation time that we observe, which is maybe common for these type of large earthquakes in a region like Tibet. So that's what I wanted to say, and these are my conclusions. The Sentinel average velocity map of this 8 years time period reveals some interesting behavior along the faults. The Altintag rate seems to decrease in 2 steps along the fault. It's not a continuous decrease, it's really 2 steps. And the one in the east corresponds to the branching off the thrust fault in the Chilean mountains, but the one to the left may be related to the stress shadow effect of the Kunlun fault, including its past seismicity. This is something which cannot be permanent, because that would make topography developing between the 2 faults, and that's not what we observe in Tibet. The post-Kunlun earthquake rate on the Altintag seems to be lower than the rate observed on the Altintag before the earthquake, and it suggests that the Altintag may respond to the stress change produced by the earthquake on the Kunlun fault. And that's going to be the goal of the future work, is to understand what type of rheology we can infer on the deep part of the fault to respond to small stress change occurring due to the earthquakes on nearby faults. So thank you very much, and let's next month.